Hello there, chemistry students. Today we have another lecture. It is the second lesson in our acid and base unit. And today we're going to be talking about the pH scale and acid-base indicators. Our aim today is going to be to determine substances to be acid or basic. How are we going to do that? So let's review the properties and theories of acids and bases that we learned in lesson 1. We learned about two different acid-base theories from different scientists. The first being Arrhenius, Arrhenius theory of acid and bases. So Arrhenius came up with this theory based on aqueous solutions that acids always contain a hydrogen ion. You can see in the examples below that we have hydrochloric acid, and it dissociates into hydrogen and chlorine. So a hydrogen ion and a chlorine ion. And then we also have HNO3, which dissociates or separates in aqueous solutions into a hydrogen ion and NO3 minus. So both of these examples, we have hydrogen ions that are dissociating out of these compounds. They're separating out. Now, in Arrhenius's base theory, we are saying that bases will always contain an OH ion or a hydroxide ion. NaOH will dissociate into sodium ion and a hydroxide ion. So you can see that it has that OH right there coming out. Now, there's another theory, the BNL theory, or Bronsted and Lowry, acid and base theory. Now, this theory dictates that acids are always going to be proton donors or hydrogen ion donors. And remember that a hydrogen ion, it's just going to be simply a proton and an electron. So it's positive because it only has a proton and an electron, or rather, it is just a proton right here because it's a proton. Anyway, the bases are going to be proton acceptors where they're accepting the hydrogen ion because it actually doesn't have an electron. It's just a proton all by itself because it's positive. So we are taking these protons and we are accepting them if we are BNL bases. So Bronsted and Lowry acids, they are going to be giving away their hydrogen ions. And Bronsted and Lowry bases, they are accepting extra hydrogen ions that might be in the solution. In the example below, we had it in our previous lecture, we have hydrochloric acid, and it is going to be added to water. What's happening here is because hydrochloric acid is an electrolyte, it's going to dissociate. So Arrhenius says that what contains hydrogen ions will be an acid. So in this case, if we dissociate or if we separate hydrochloric acid, what will we get in return? And you see the reaction below. You have hydrochloric acid and it dissociates into hydrogen ions and chlorine ions. Now, on the other hand, Bronsted and Lowry, they say that if they are able to accept a hydrogen ion, this means that it is acting as a base. So if something is able to accept a hydrogen ion, therefore it's going to be a base. So in the example that we see right here, which one is accepting a hydrogen ion? All right, let's continue on. So now we know how to identify them in a chemical reaction. So how do we determine if we have a substance in front of us, if it's going to be an acid, and which one's going to be a base? So we've heard of something that we've used in science before. I guarantee all of you have heard of pH. Now, pH is simply measuring the amount of hydrogen ions or hydronium ions concentrations within a solution. So how much hydrogen ions do we have floating around in the solution, or how many hydronium ions we have floating around in that solution? So a pH scale, it ranges in value from anywhere from 0 all the way to 14. Now, acids and bases can be identified by their different pH values. And we're going to be using the pH scale that you kind of see before us with these examples throughout the lecture. So acids on the pH scale, they're going to have any value that is less than 7. So anything that's below pure water on the pH scale, 6, 5, 4, 3, 2, 1, and anything below 1 is going to be acidic. In contrast, bases are substances that have a pH with values more than 7. So anytime you have a pH above 7 going this way towards 14, that's basic. Now, if you have a pH that's exactly 7, that's considered neutral. And there's only a couple different substances that have this. Mainly, we go with distilled or pure water. So let's think about this for a second. So we're going to have to also mention that the hydronium ion and the hydrogen ion is pretty much the same thing, because in a solution, all that we're going to be having is hydrogen ions attaching to water. That creates a hydronium ion. So hydrogen ions floating around and hydronium ions are the same thing. But what about, can we measure the pH value of NaCl, which we know, remember, is salt? Do we find that on the pH scale here? No, you don't. So how strong can an acid and a base be? Well, we have strong acids. They have very low pHs. So anytime we have something in the low pH range, that's considered to be a very strong acid. For instance, your stomach acid is around 1, which is actually almost the same strength as some battery acids. So you can consider your stomach acid or your gastric acid to be relatively a strong acid. In contrast, strong bases have a very high pH level. So over here in the 12, 13, 14 area, bleach and also some like drain cleaners have really high pHs as well, and even some concentrates of vinegar. So let's have a quick learning check to see how you do. Which of these pH numbers indicates the highest level of acidity? Now think about this for a second. Is acidity going to be a low number or a high number on the pH scale? So we have the answers of letter A, 7, B, a pH of 5, C, a pH of 10, and D, a pH of 8. Number 2, a compound whose water solution conducts electricity and has a pH of 9 could be A, HCl, B, NH3, C, LiCl, D, C2H5OH. Number 3 says, which aqueous solution would have a pH of 3? Now, once again, remember, for these past two questions, is a pH of 9 basic? Is a pH of 3 acidic or basic? What are we looking at here? The answers are letter A, H2O, B, CH3OH, C, KOH, or D, HNO3. And these are all found in an aqueous form except for letter A. Moving on to number 4. Which solution could have a pH of 10? Is 10 going to be acidic or basic on the pH scale? Letter A, NH4OH. Letter B, NaNO3. C, NaCl, which is salt, as we remember. Or letter D, Na2SO4. So remember to be using your periodic table for these questions. Look at the tables that dictate common acids and common bases that we can find. So we're going to move on to acid and base indicators. So indicators are substances that change color in the presence of acids and bases, and common indicators are always going to be listed on table N. But you're probably asking yourself, where is table M? Well, I got a surprise for you. It's right here. And if you need to find it, you can always read table M in your periodic table of elements that we have listed in the reference guide, right in your Google Classroom, right in the guide. So let's go through a couple of examples. We're going to look at methyl orange first. So what happens if we have a pH that is below 3.1? Yeah, methyl orange is going to be red, because you can see right here that if it's going from 3.1, a high acid, meaning a low pH, to a 4.4, we're going to see a color change of red to yellow. So if it's below 3.1, we are going to have a red color. But what if it's above? What color will it be then? Yeah, if it's above 4.4, we're going to see the color yellow from methyl orange. What about thymol blue, the bottom indicator right down here? It's good between the pH range of 8 to 9.6. So if we have a pH of 8, what color is that indicator going to show up as? Yeah, it's going to show up as 8, being yellow. Now, what happens if it's above 9.6? Yeah, it's going to come up as blue. So commonly used acid and base indicators that you would have seen in lab, or that you might still see just around, are going to be phenolphthalein. It is a colorless indicator solution, and acids will actually have no effect on phenolphthalein. So if you had just had a regular aqueous solution and then you added in HCl and it became acidic, and then you put phenolphthalein in as an indicator, it would actually be colorless and you wouldn't see anything. But in the case of a base, we're actually going to see a change to a pinkish color. Now, we also call basicity or base alkali. You can see that on the side right here. It says alkali. That just means base or basic. So litmus paper. Acids will change litmus paper to red. And in contrast, they will change in the presence of a base, they will change to blue. And you probably have seen these actually used before in swimming pools. Like a lifeguard might go up to the edge of the swimming pool and put a little strip of paper into a sample of the water and then wait for it to change. They're actually using a piece of litmus paper. Let's have another quick learning check, and we're going to have this learning check based off of these indicators. So make sure you remember that phenolphthalein in the place of an acid will show clear, and that bases will appear pink in phenolphthalein, and with litmus paper, acids appear red and bases will appear blue. So, for number 1, an indicator is used to test a water solution with a pH of 12. Is a pH of 12, is that acidic or basic? Which indicator color could be observed if we have a pH of 12? And what's our indicator? Let's find out. Letter A, colorless with litmus paper, red with litmus paper, colorless with phenolphthalein, or pink with phenolphthalein. What do you think? And number 2, in aqueous HNO3 solution, phenolphthalein will turn what? So phenolphthalein will turn pink and litmus paper will turn blue for letter A. Letter B says that phenolphthalein will change pink and that litmus paper will be red. And letter C says phenolphthalein will be colorless and litmus paper will be blue. And letter D says that phenolphthalein will be colorless and litmus paper will be red. So make sure you're looking up HNO3 and you're thinking about what happens to different indicators here. Okay, everyone. Well, thank you very much for listening in on this lecture. As always, reach out to us with any questions or comments you might have about this content. Thank you.